All right, so what I want to talk about today are the inherent limitations of current computation infrastructure and the shift towards the neuromorphic computing paradigm. Before I'm going to talk about precisely what neuromorphic computing is, I want to take back a step and kind of motivate or talk about why this shift towards neuromorphic computing is unavoidable. What is happening today in all our aspects of our lives, in business and in science, is that there's a profound technology or technological transformation. Scientific breakthroughs in recent years have made it possible for us to have much more devices around us, devices that record data and store data and collect data at a much higher rate, at a much higher precision than ever before. The example here shows how by increasing the resolution of telescopes, we put out a new telescope every couple of years, we can increase the resolution, we get more data, we can process and analyze the data and then illustrate what is actually happening. We can illustrate natural phenomena in much greater detail and we can better understand it. And we're all part of this revolution, of this change. Everyone is generating data by clicking through the web, by having sensors around us, many more sensors, much higher resolution, much higher rate at data acquisition. We generate massive amounts of data, and this is a tremendous opportunity to analyze this data, to process this data in order to understand the world around us better. What this graph here shows is how the amount of data we are collecting is growing rapidly. It's not just a linear trend, but the trend towards storing more and more data is actually accelerating. And this is all data that we don't just want to store. Storing data today is fairly simple. Technology is cheap, but analyzing this data is incredibly hard. The fundamental problem is that we see a gap between our capabilities to analyze the data as well as the data that we collect and that we want to analyze. The green line is still how the amount of data are growing that we are collecting that we want to analyze. And the blue line is showing the chip technology as it advances. Moore's law says that every second year, every other year, we double the number of transistors on the chip. But as this graph tries to illustrate, that's not good enough in order to scale up to the amounts of data that we are collecting today. So what is the issue with this computing technology? And I'm focusing here mainly on chips. Similar principles apply to storage, to networks, to main memory. So what is the issue with current technology? The problem fundamentally is that today's technology, chip technology primarily, cannot scale. There are many issues why it cannot scale. I want to just focus on pretty much three of them. I want to highlight three of them. The first issue is energy consumption. Today's chips need too much energy. Yes, indeed, we are doubling the number of transistors every year, but we can't get the energy into the chip to actually operate the entire chip. So at any point in time, only parts of the chip are going to be used, leaving the rest in the dark, and that is also what we call dark silicon. A related issue is the one of heat. We double the number of transistors. Transistors get smaller. So in the same space, we're producing much more heat, and getting this heat out of the chip, out of the computational infrastructure, is an increasing problem. It's also evidenced by the fact that today, when you run a data center or a supercomputing center, a huge fraction of the bill is going to be the power for the cooling system. This is something that limits today's technology. And then finally, very important for data analysis, the memory bandwidth. Chip technology improves, but the memory bandwidth does not keep up. And so we can't get the data into the chip at the rate that we need to in order to process and analyze the data that I've been talking about just before. But we do care about this. We really want to analyze the data. It may hold very interesting insight in business. We want to understand customers. We want to understand the business, or also in science. So we want to analyze the data. We need a scalable solution to technology that helps us analyze the data. And this applies, like I said, to business. This applies to science. I'm going to make 4 examples from science. For example, next generation sequencing. We have better tools that sequence DNA at a much higher rate, at a much higher precision, much cheaper. And that leaves us with a lot of DNA sequence that we need to analyze in order to understand it, right? The next example is astronomy. Like I said, we are deploying a new telescope every couple of years. The Square Kilometre Array telescope is supposed to become operational, I think, in about 3 years. That will have a high resolution. It will produce 1 exabyte of raw data per day. And this is all data that we need to sift through, that we need to analyze in order to better understand astronomical phenomenon. Then also in geology, we want to sense the Earth at a much higher precision, leading to more data in order to find rare minerals. And then finally in computational science, where we want to simulate natural phenomenon like the brain, like cell-cell interaction. There we're increasing the size, the power of the computers that we use to simulate, and that also increases the amount of data that we are collecting. That increases the amount of data that we need to analyze. Now, the problem is, like I said, our current technology doesn't scale very well. One central issue is the von Neumann architecture. Chips and in general hardware has been developed around this architecture, which is very, very centralized. And this has given us tremendous results in recent decades. We have fundamentally, we have very powerful computers, very powerful chips, but the problem is this centralization no longer scales. Von Neumann architecture essentially stipulates that resources are centralized. For example, main memory is in one central place, so that means the data is in one central place. And so all the chips will access it at the same time, creating a bottleneck, and that's what makes it difficult to scale. So how can we overcome this? Because we want to find interesting pattern in vast amounts of data. So what we were thinking is, why not make computers, hardware and software, more like the brain? And that's what is called neuromorphic computing, essentially. So why do we think that? Well, the brain is really, really good at trying to, or finding interesting patterns in a lot of noisy data. And that's what we're collecting, a lot of noisy data, right? So what we know about the brain, or why it is good, is because it basically distributes the memory, right? As opposed to the von Neumann architecture, right? It basically stores information in neurons and synapses all across the brain. So it decentralizes the information, which is a good thing, right? The brain also works massively parallel, has quite a parallelism in that every neuron works in parallel with each other, right? Fires signals to each other and so on. It's also very energy efficient because the neurons are quite simple. They don't do much. They just add up incoming signals and fire out new signals. And so with that, it becomes a really powerful machine, a really powerful device to find interesting patterns in noisy data. We don't know everything about the brain. We know a couple of things about it. There's still a lot more to explore, but we know one important, really important thing. That is the one of massive parallelism, right? In today's chips, in today's computers, we see a parallelism maybe of tens of cores, maybe hundreds, no more than that. And that means we have to solve problems in a lot of processing steps. The brain has a much higher, orders of magnitude higher degree of parallelism. Like I said before, all the neurons fire in parallel and work in parallel and solving the same problem. And that means we need fewer processing steps. That means we can solve problems, find patterns faster. So how do we do this? How do we translate this neuromorphic computing idea into hardware and software? We need to define new or design new hardware for that, as well as new software, new algorithms for that. The hardware, I want to spend a little time on that. This is not just a vision. Neuromorphic hardware exists today in research prototypes from the University of Manchester, for example, Heidelberg as well, but also products from IBM, True North, from Intel, we have Qualcomm, and also Apple recently announced the idea of launching a neuromorphic chip. The way all these different products and prototypes differ in how they're implemented, but the fundamental principles are the same. Massive parallelism. We don't have tens of cores, we have hundreds of thousands of cores on these devices. So right now we're looking at the size of 500,000 cores, 500,000 cores working in parallel. Each core is very low powered, very similar to the brain, where the neuron is not doing really much. That saves a lot of energy. And then very importantly, also the memory is distributed across the cores, very much unlike current technology where it's typically sitting in one central place. And then one also very important point is better connectivity, in the sense that very much like the brain, we want to connect neurons. Here, we want to connect cores. So we need to have better mechanisms, better networks, on-chip networks that connect the cores so that we can work together, the cores can work together on the same problem. So the hardware is there, but the software isn't quite, and that is essentially what I'm working on. So what I want to do is develop the software to run on neuromorphic hardware, massively parallel. We understand reasonably well how to write parallel code for tens of cores, but doing so for 500,000 cores is a different problem altogether. And so what we're trying to do is find or develop new algorithms, new software to find interesting patterns massively parallel on this infrastructure. What we also need to rethink is how to kind of the programming tools, the programming paradigms that help us to do that. Because like I said, we do know a little bit about how to program on tens of cores, but doing so on hundreds of thousands of cores and in the near future, 1 million cores, that is a different challenge. Now, why does it help, or what does it do? Well, the neuromorphic hardware taken together with the software will allow us to find patterns in very noisy data, very efficient in terms of time and in terms of energy consumption. There's still a couple of hurdles that we need to take. For example, when it comes to software, like I said, we need to parallelize the problems. Some problems are inherently or difficult to parallelize. And there we need to find new programming abstractions that help us to understand these problems as massively parallel. In terms of hardware, we need to improve the connectivity between the core. We need to improve the network such that the cores can communicate with each other. And we also need to develop better means for fault tolerance. Because if you operate something on 500,000 cores or 1 million cores, some of them will fail, and we need to account for that. That is not trivial. So with that, I'd like to come to the applications that neuromorphic computing has, what we can actually do with it. The most the straightforward application is to simulate brain activity. And that's what we're already doing today. On the hardware we have, it doesn't allow us to simulate an entire brain, but it allows us to simulate part of it. And that actually allows us to better understand the brain and then feed this back into building better neuromorphic hardware. But more importantly, it also allows us to advance medicine. What we can do is we can simulate a diseased brain, we can simulate a healthy brain, and if we do this for the diseased brain, we can simulate disease progression, we can better understand how the disease evolves over time. We can also simulate medication, treatments. For example, depression. One of the causes of that is a neurotransmitter that doesn't allow the neurons or the synapses to fire fast enough. This is something we can easily simulate on this neuromorphic hardware. In a similar vein, I am working in my lab with collaborators in neuroscience on better diagnostics for brain diseases. What we want to do is find these kind of objective definitions of disease, these kind of signatures of disease. So one of the problems of, for example, the one we're working on right now is Alzheimer's. One of the problems of these diagnostics is they are inherently unreliable because a lot of the symptoms are the same for different forms of dementia. And typically, we can only certainly say if somebody suffered from Alzheimer's post-mortem, which is obviously too late. So what we try to do is we try to analyze the wealth of data, medical data we have available, and we try to find interesting patterns, interesting signatures of disease so that we can look at the underlying causes and then treat patients better. We're working on that. We expect this to have results to improve the accuracy of Alzheimer's diagnostics in the very near future, and then we move on to other brain diseases. Further down the line, a similar idea is kind of to develop these signatures for personalized treatments. such that we can, again, analyze medical data using neuromorphic hardware and software and find these patterns that define the disease. It's a huge trend in medicine altogether, is to move away from symptom-based diagnostics to actually understand and characterize the root causes of the disease so that we can better, more targeted treat the disease or even offer personalized treatments. Further down the line, population health, we want to understand how or find characterizations or disease signatures or kind of patterns that define infectious diseases, and in order to control and contain them. Another example is cybersecurity. Here we want to be able to understand that that's what neuromorphic computing can do for us, is we want to classify what exactly is happening in the network. Is it a buggy software? Is it buggy software that basically causes anomalous behavior, or is it indeed a cyber attack? And that then helps us to tackle that, right? Similarly, we want to be able to tackle major meteorological events. We have wealth of meteorological data that we want to analyze and find interesting patterns that then predict near-term future so that we can act on that. Similar in financial data, the patterns repeat themselves. We can identify these patterns and then foresee risks and work around them. A big topic is edge-based AI. That's going to happen in the very near future because, like I mentioned, Intel is working on neuromorphic hardware, so is Apple, so is Qualcomm. And what they want to do is essentially put these neuromorphic chips on our mobile devices, on our mobile phones. The idea being that what's happening today, for example, if you use AI on your phone, typically a lot of the data is going to be uploaded into the cloud and you get the result back. The idea of edge-based AI is to run this on neuromorphic chips on the hardware itself. So for example, the US Army is looking at putting neuromorphic chips on their soldiers within about 10 years. They want to do this to make it possible for them to sense the environment around them, find interesting patterns, find dangers, find opportunity, feed it back to the soldier so they can act on this, upon this information. And the reason to use neuromorphic hardware is because it makes the system autonomous. It means also that it's energy efficient and soldiers don't have to carry around as many battery packs because it is very much energy efficient. And we see this also, there's also civil applications of this, essentially where we have cyclists or motorists who sense the environment around them. Neuromorphic hardware is going to help them to identify dangers, pedestrian crossing in the street and so on, and it's going to alert them to that so they can act based on that. Another application is direct translation, where we talk into the mobile phone. The AI running on the neuromorphic chip will translate directly in real time to the user, right? And this is going to happen in the very short term because, as I said, hardware companies are working on putting this kind of intelligence, if you will, or neuromorphic hardware onto our mobile phones. But it's always going to be us who is in charge. That's at least my opinion. The computers, neuromorphic computing, is going to feed us information, is going to identify interesting patterns for us, but it's always going to be us who makes sense of this and it defines whether or not the pattern that we're interested in is useful or useless. And so we are going to be in control. And that's also very much our approach to work on diagnostics. We're not making any decisions. We're giving the doctors new tools to improve their diagnostics. We're giving them more information. We're giving them a better basis for a decision that they then can make, right? Now, I talked about this hardware and neuromorphic computing as also a software problem. Right now, we're very much at the beginning of this. We have chips and systems that go up to 500,000 cores. With that, we can maybe simulate a couple of million neurons. With that, we can pretty much get in the area of a neocortex of a rat or a mouse. That's not very useful as such. We want to understand the human brain better. Maybe also the rat and mouse brain, maybe there's applications there as well. But in order to scale things up on a truly human level, or even beyond that, there are several challenges ahead. We need to find new architectures The interconnectivity in the chips we're using so far is far better than in traditional computing, but we need to go way beyond that, so we need to work on architectures and also materials to improve that. Programming models, programming abstractions are also quite difficult to develop. I'm not just saying this because I'm doing it, but it's really truly a challenge. We need to rewrite most of our software to work on this level of 500,000 cores and beyond, and millions of cores in the near future. So we need to find new tools, new programming abstractions to do that. And then lastly, neuromorphic computing will help us to offload some of the cognitive load we have. So neuromorphic computing will sense the environment around us, will identify patterns, dangers, opportunities, and so on. That needs to be fed back to us. Augmented reality does this through visual cues, through audio cues, but in general, we need to find a way to interact with this hardware and with this new idea of neuromorphic computing. And so finally, what we have traditional computing, which is fantastic at precise calculations. I wouldn't be able to do that, right? And that has been tremendously useful in the past and will be useful in the future. Now we have neuromorphic computing that is fantastic at finding patterns in vast amounts of noisy data. If we take this all together, we take traditional computing, neuromorphic computing, combine everything together, then we will actually, with our brain, then we actually have a super brain. Thank you very much.
Thomas, a couple of questions coming in. Say whether you can offer an answer. Here we are. Quantum computing versus neuromorphic computing. Which is the winner?
Depends on the task.
Thank you.
And I have to say that, no, it's going to be neuromorphic computing, of course. No, but the question is really, it's about the task, right? I think quantum computing has the potential to replace traditional computing in terms of scale, in terms of precise computation, but this notion of going through noisy data, this is not a problem that quantum computing will fundamentally solve. I think that's where neuromorphic computing has the edge. And I think I'm not somebody who's going to say neuromorphic computing is going to replace traditional computing infrastructure. Not at all. It's going to complement it, and we need all of it.
Right. Okay. Just a couple of other questions. Could neuromorphic computing pose a risk to encryption in the conventional computing arena?
No. Quantum computing will, but not neuromorphic computing.
Right.
I think it's really about, we won't be able to do that at a scale that will actually really make the danger for encryption.
Right. Interesting one here. Are brain diseases really classifiable as distributed software problems?
Yes.
Neuromorphic signatures. Give us a couple more words on that.
No, absolutely they are, right? I mean, what we're trying to find is really, so the way we do this is we take medical information, medical data from patients, MRI scans, blood tests, and so on. We try to group them together, and that is something we try to cluster the information, find commonalities between different patients who have the same disease. And that is very much a problem that we can easily parallelize. Well, I'm not going to say very easily, but this is something that we can work on, that we can scale very, very well.
Okay. Just one other one at this stage. I mean, we still know so little about the brain. I think 1% or whatever. Interesting question from Michael. If we're talking about scaling neuromorphic computing to the scale of the human brain, what are the implications for emergent properties like consciousness?
Well, that's going to require more than one word. So the consciousness in neuroscience is typically called the C word because nobody really wants to talk about it.
Right.
The problem is we don't really understand consciousness, so we don't know when we will actually get to that stage. But the best bet we have is build a machine with the same number of neurons that humans do. We replicate it as much as we can, and then we actually try to see whether or not it gains a level of consciousness that we can recognize as such.
Right. Okay, thank you.
Thanks.
Fascinating stuff, and we'll have you back shortly. But for now, Thomas Heinis, thank you very much.